Hey guys, how's it going?
All right. How about you?
Could be better. We had a faculty meeting today. Well, we got chewed out, so I'll say that.
What happened?
You know, in the interest of, you remember when our guest speaker says you shouldn't say bad things about your boss?
Oh.
Well, we'll leave it at that.
Was it us?
No, it's not you guys, no. Honestly, you know, I've told people this, but you know, there's a lot of challenges to this job, but my favorite parts are when I get to spend it with you guys, the students. And so, you know, but everything else is difficult. You know, I love being in the classroom, you know, I love being with you guys, and that's what I signed up for, and you guys are always there for me. So I appreciate that.
We were leaving the room and so she stood to go open and like just walks right into it. Like it was loud. No, I like it. I can't see it. But he was like right against the door too. That's also run. Like, what? Did you tell her to put run? No. Explain it. She texts me, so I'm not sitting with them because I couldn't see them when I got across. She texts me, she goes, "Want some cheese?" And I thought they were at a store. No, I'm just like, so they were a normal spot. And so I'm with a friend, so I don't see them put on my glasses on. So she's texting me about cheese, and I was like, "What store you guys at?" No, it doesn't matter. She's on the phone. I was like, "What store you at?" So I know what kind of cheese. You don't get time.
What?
We're playing musical chairs. Your new friend is Etienne.
Sit down.
So sorry for
Why?
for couple.
Yes.
Yes, it is. Yeah, it's still a latte. It looks disgusting. They did it with instead of cooking. It's like a weird because it's gross. It's a weird color. That's what's good, but it's a weird taste. That's such a good place. It looks weird with heavy cream, and you goes, "What does?" I said the features like 4 times. It's weird. Professor, you want a muffin?
Oh, no, I'm good. Thank you, though. I had a late lunch, so I'm pretty full right now.
It's secretly a strawberry. I just like open the can. Gotta keep them fresh.
Just talking to somebody. They started talking about like.
He's not comfortable. Just call it a They have the white one sugar free. Serious, not sugar free.
Where's it go?
It's got 2%. This one was sugar free. Oh. I get a lot of I don't get a black tea with 2% and vanilla. It's like it tastes the same. Yeah, but I don't get it in a black 2% milk. I get it in a lot of big difference too. I only get it in this. You're like, no, what is it taste different? It's a
All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Hanging in there, end of week 8. So one more week and we have spring break. So that's a be a fun thing. Okay, so the plan today is we're going to start a new set of lecture notes. Okay, so this class is kind of interesting because it kind of rubber bands kind of between kind of what we just finished, which is I think some really cool like biological kind of applied stuff, back to some really intense math stuff. And so this This lecture and the next one's going to be a little bit heavy on the math, but you know, it's all in the same vein of model. Okay, and I placed this lecture kind of very strategically throughout the class because we had just finished talking about lump parameter modeling, and then after the spring break, we're going to talk about CFD, computational fluid dynamics. Okay, and so these techniques are kind of in between those two, and so you know you'll see what I mean more when I start with the lecture. Okay. All right, and so other announcements I want to make is that make sure to fill out the poll, or not really a poll, but make sure you choose the type of model that you want to work on for your final project. So I believe that's due tomorrow. So I haven't checked the results yet, but I think probably starting tomorrow, I'll have a bit more time tomorrow because I've been a bit busy this week. I'll start sending out medical image data tomorrow, and so if you fill it out by tonight, then you can get started on the project tomorrow. This weekend, I might have some time to fill stuff out. And so if you send stuff out, so if you fill it out, you know, late tomorrow evening, you know, I might be able to get to you over the weekend, but if you get it in by tonight, then I can start sending the stuff out tomorrow. Okay. All right. And so I think that's all my announcements. So are there any questions I can answer before we get started? Yep.
Will you be making more workshops?
Yes. Not about the model building. And so the model building we're basically done with. But after the spring break, we're going to have a workshop on running simulations. And so you know, we're going to have a couple lectures just talking about what CFD is in general. And then we're going to have a workshop to show you how you actually accomplish that within Vascular. Yeah. And then after the spring break, you know, because the simulations are a bit too heavy to run on your home computers. And so I'm going to get everyone accounts onto a supercomputer. So you can run the simulations on that. Okay. All right. Any other questions before we get started? Okay. All right. So let's go ahead and get started. All right. So the title of these lecture notes is called the 1D. I call them the 1D blood flow equations. Okay. Which makes it not seem that scary, because when you talk about things in 1D, you know, you're usually not too scared of it. Because 1D means there's just one dimension, right? And so if you're solving things in one dimension, you know, that's usually pretty doable. But what you'll see as we go throughout that it's a bit more complicated than that. Okay. Okay, so let me start off by saying that, you know, we've started you know, we started kind of this modeling journey by talking about lump parameter models, right? Right. And so just to remind you, these are circuit element representations of our cardiovascular system, right? And so instead of a blood vessel like this, okay, you know, we would instead replace this with something that maybe look like that, right? So we have a capacitor and maybe we have an inductor right there as well, okay? All right, and so what we solved for was not, you know, not a fluid mechanics equation, but instead we were solving for a circuits type system, okay? And if you remember, you know, the main advantage of this, or the main reason why we'd want to do this, is that circuits are usually a lot easier to compute, a lot easier to solve than, you know, a blood vessel, right? Okay. Right. And so what we saw was that a circuit would be governed by a set of ordinary differential equations, and you know, first of all, you can solve a lot of these by hand, but even for the ones that are a little bit too big to solve by hand, you could solve them with math. Right. So we saw how that can happen. Okay. The downsides to LPN, and I would say its biggest downside, is its lack of spatial resolution. Okay. Okay. And what I mean by that is that you can only solve for quantities at you know, certain locations on the circuit. Okay? And so if we were interested in the pressure, you know, the only place where we can compute pressures is right on top of a capacitor, right? We can't really compute pressures anywhere else because, you know, we just don't solve for anywhere else. Okay? By the same token, we can only solve for flows on an inductor. Okay? We can't solve for flows anywhere else, you know, because we just don't have an equation for it. Okay? Resistors are a little bit special because that you can kind of solve for, you know, kind of both on a resistor, but even then you're kind of limited. Okay. But the thing is, you know, with blood vessels, you know, oftentimes we're not just interested in distinct locations. Oftentimes what we're interested in is, you know, how does this quantity, like how does the pressure vary along the entire length of the blood vessel, right? And so as an example, you know, let's say that, you know, we have this blood vessel here, you know, we kind of trace a path down the center line of the vessel. You know, what we may be interested in is like, you know, if I call this the Z direction here, okay, so the Z direction being down the length of the vessel, okay, we might be interested in seeing, you know, what's the pressure as you ride along this vessel, right? And we want that expressed as like some kind of function like this, right? The difference between what we have on the left and what we have on the right is that that function gives us a lot greater spatial resolution, right? And sometimes that can be desired because, you know, there are these situations if you have, you know, say a patient with a disease. So maybe a patient has high blood pressure, right? And you want to see how their pressure varies in their system. Or maybe they have a stenosis, some kind of atherosclerotic plaque, right? You want to see how their pressure varies as you go through stenosis. Or maybe they have an aneurysm, right? So maybe you want to see some detailed information on that. And so you kind of miss all of that in the lump parameter models, okay? And so this kind of you know, makes it seem like we want something more. We want a little bit more detail than our lump parameter models, okay? But at the same time, you know, we don't want to solve the full Navier-Stokes. So if we want to solve the full Navier-Stokes, then we have to rely on CFD. Okay. And so just like I talked about, you know, at the beginning of class today, right? So if you were to run a full CFD, you know, most of the time it's going to require some kind of supercomputing, right? So that's a lot of CFD just is not feasible to run on a desktop computer, okay? And so you're going to need dozens of processors, sometimes hundreds of processors in order to accomplish that. Okay? It's you know, as kind of a side note, you know, it's really interesting to me that a lot of people seem to be really interested in computer power consumption now because of crypto. And so for people that have worked in high performance computing, like running CFD, you know, they've known for a long time that, you know, the power consumption for a simulation process is pretty high, actually. It's a lot higher than you would think. But now that crypto is becoming a big thing, you know, everyone's kind of has an opinion on it now. So it's interesting. And so I know most of the conversations are about, you know, how do we make crypto not so power hungry, but that kind of applies to CFD as well as some other simulations. Okay, so back to the scheduled programming, and so this kind of, you know, makes us want some kind of in between you know, full-on CFD and lump parameter models. Okay, and that in between that we have is our 1D equations of blood flow. Okay. And so, I've been saying that these are the 1D equations, 1D, 1D, but, what does that exactly mean, right? Because when we think of 1D, you might think of something like, like we're solving something just along the x-axis or something, right? That's what you think of when you think of 1D. And so the 1D here is a little bit different. And so it's not exactly along a coordinate axis, but the one dimension that we're going to be solving for is along the center line of the vessel, okay? And so basically, we're going to be mapping quantities to that center line and then plotting those quantities along that center line, right? And so even if you have a vessel that, maybe does something crazy like this, right? So let's say we have a vessel with a relatively curved path, okay? Right? This might look like a very two-dimensional structure or even 3 dimensions. It comes in or out of the page, right? But if we trace a path along the center line, right? And I'll call that center line dimension Z, as is traditionally done, okay? What we can do is we can plot quantities along that center line, right? As if it were a 1D situation. Okay? So maybe we have some of the pressure and it's plotted along the center line, okay? And so that's what I mean by 1D. And so the 1D refers to the center line coordinate. The vessel itself may not necessarily go in a perfectly straight line. Most of the time it's not going to. But if we keep that center line as the dimension that we're interested in, we can plot things along that line. And that's our one dimension, right? And it's kind of good that at this point kind of everyone's done this vascular tutorial. So everyone's kind of familiar with the concept of like a center line path. And so think of if you think back to when you did the tutorial and you looked at all your center line paths, think of plotting pressures or plotting flows along that path, and that's essentially what we're going to be doing here. That's what we're going to be solving. Okay. All right. Any questions on this? Okay. All right. And so how are we going to get these equations, right? And so the starting point for these equations actually will be the Navier-Stokes equations, okay? Okay, and so we're going to start with the Navier-Stokes equations in cylindrical coordinates. But what we're going to do is instead of solving those equations straight up, we're going to integrate those equations across a vessel cross-section before we do any solving. Okay? Okay. And integration buys us something really nice, because when you integrate a function across a certain variable, then it effectively eliminates that variable from your equation, right? And so as an example, let's say that we have a 2D function, right? XY, and let's just say it's x squared times y, right? One way that we can eliminate the, one of these variables is to just integrate over them, right? And so if we take the integral, so let's say we take the integral from 0 to 3 of f of xy with respect to y, okay? What we get then is integral from 0 to 3 of x squared y dy, okay? We integrate this, we get x squared y squared divided by 2, evaluated from 0 to 3, okay? We plug that in. I always do this. I always do something that's not a perfect integer, but that's okay. Right, and so we plug that in and we get x squared times 9 divided by 2, okay? And so by performing this integral over the y component, we effectively eliminated y from the equations, okay? And so we're gonna do the same thing with Navier-Stokes, okay? Because in cylindrical coordinates, our velocity, okay? And let's just take one component of velocity. So let's say it's the axial velocity down the length of the cylinder. It's going to be a function of r. It's going to be a function of theta. It's going to be a function of z. Okay. And in this case, since we're not going to assume that it's steady, it's going to be a function of time as well. Okay. And so that's a lot of variables, and that's part of the reason why Navier-Stokes is so difficult to solve, is because there's lots of variables that the velocity depends on. Okay, and so what we're going to do is, what we say is the radius and theta. We can integrate these out by integrating over the cross section. Okay. Okay, and so in the end, we only get a function that's a function of z and a function of time. And the fact that we only have one spatial dimension left, which is z, that gives us the name 1D blood flow equations. Okay. All right. Any questions on this so far? Okay. All right. And so by performing the integral, we actually transform our quantities. And so we're no longer solving for the velocity, right? And so by integrating, we kind of change, what our unknown is going to be. Okay? And so instead of velocity, we're going to be solving for flow rate instead. Okay. And so we have a function of q, which is a function of z and t. Okay. We're going to be solving for pressure as well. Okay, so pressure, and so we'll give that the symbol p as a function of z and t. Okay. We're also going to solve for one unexpected quantity as well. Okay, so by integrating, we naturally are going to be solving for area as well, right? And so the cross-sectional area will actually also be an unknown that we're going to solve for. Okay, which is very strange because usually you don't solve for area in these types of equations. But what you'll see is that once we start kind of deriving these equations, it comes out, very naturally from that. Okay. All right, and so what are the advantages of this? Right, and so I think one of the primary advantages of the 1D equations is its spatial resolution, okay? Spatial resolution relative to the cost, right? And so the only spatial direction that we have to worry about is just the centerline path, right? And so just the centerline direction. And that has a lot of benefits for our system because, the cardiovascular system, the geometries, yes, are very complex. But generally speaking, if you had to rate, if you had to kind of rank the different dimensions in terms of which ones are the most important, the centerline direction is by far the most important, okay? And so if you compare, how things like pressure, how things like flow, how that change as a function of centerline versus the radial direction and the polar direction, things are going to change much more in the centerline direction. Okay, and so by limiting our solution to just that, we're really making really efficient use of our efforts, of our mathematical efforts. Okay. And so, of course, it's not going to be as accurate as full CFD, and it's going to take a lot more effort than parameter modeling. But I think this gives a really nice compromise of what's really the most important direction in the cardiovascular system. Okay. Okay. Number two. So number two, one of the nice things about 1D equations is that it actually lets you solve for deformable walls as well. Okay. All right, so there's a question in the chat. So the question is, does SimVascular work on 1D blood flow principles? So the solver that we're going to be using in SimVascular is actually going to be a full-on 3D CFD solver. So that's the one I'm going to have you guys work on for your projects, just because, I think you guys don't, people generally don't have the opportunity to use a full CFD or use a supercomputer for that matter. And so I thought that would be a cool thing for this project. But SimVascular does have the capabilities to do 1D. If you remember, when you downloaded the SimVascular software, there was another software there called like SimVascular 1D Solver. And so that's what this is basically. But I'm going to have you guys do the full 3D CFD. Yeah, it's a lot more fun to do 3D CFD than 1D. Okay. But one thing that the 3D CFD won't be able to do is deformable walls, and so I think that's one of the nice things about 1D equations. Okay. Okay, and so the deformable walls comes in the form of this cross-sectional area right here. Okay, because we're assuming that the cross-sectional area can change with both centerline distance and with time, it allows our 1D equations to kind of, expand and contract. Okay. Right, so we haven't had this before, right? And so I know we've had capacitors and lump parameter models, but capacitors kind of lump all the deformable walls into just one thing. Okay, when you have it as kind of a function like this, it allows you to see a lot of different phenomena that you haven't seen before. Most notably, wave propagation. Okay? And so out of the three main methods that we're going to learn in this class, lump parameter modeling, 1D equations, and CFD, the 1D equations are the only ones that really do wave propagation, like really naturally. Okay? You can do deformable wall simulations in CFD and 3D. And if you want to do that for your project, you're more than welcome to, but it's a little bit tricky to set up. And so I'm not going to make it a requirement, but if you are interested in learning, then I can work with you individually on that. Okay? But for the project, I just want you to do a rigid wall simulation. Okay. And so those are the two main advantages. Okay. And so what we're going to do next is we're going to jump into the derivation of the equation, where it's going to get a little bit math heavy. And so just a little warning. Okay. But that'll be the next step. And so before we do that, are there any questions on this? Okay. All right. So let's talk about how to derive the 1D equations. All right, so just like I mentioned above, our starting point is going to be the Navier-Stokes equations in cylindrical coordinates. Okay, and remember what the Navier-Stokes represents is the conservation of mass and momentum for a fluid. Okay. In cylindrical coordinates. so let's start with mass. Okay. And so the conservation of mass in cylindrical coordinates is 1 over r partial r of r u r plus 1 over r partial theta of u theta, okay, plus partial u z partial z is equal to 0. We'll start with mass and then we'll go on to momentum after that. All right. And so just kind of, so we're all on the same page, let me go ahead and draw the coordinate axes here. And so here's like a typical cylinder, or here's like a tube of blood, okay? And so when I say the radial direction R, what I mean is the direction that goes from the center of the vessel out towards the wall and back, okay? The Z direction is the one that we're interested in. And so the Z direction is known as the axial direction. And so that goes down the length of the tube, okay? And the theta direction is the polar direction. And so it kind of goes around like this. And so you can kind of imagine it coming out of the page, okay? And so it's better to view it from kind of a side view. And so, you know, on the left right there, we're looking at the blood vessels from the side. And on the right, we're looking at the blood vessel kind of straight down the barrel, okay? And so in this view, we can have the R direction like that, okay? And the theta direction kind of goes around like that, okay? And of course, the Z direction here comes out of the page. Okay. So I drew that just so that it's kind of clear what direction we're going. Okay. And of course, you know, of course we have all 3 components of velocity here, right? And so U sub r would be the velocity in the radial direction. Okay. U sub theta would be the direction, the polar velocity. Okay. So basically any velocity that kind of spins in a cross section. And of course, U sub z is going to be the velocity down the length of the pipe. All right. And so first we're going to simplify this a little bit. And so we're going to take this term right here. Okay, and we're going to set it equal to 0. And the main reason we're going to set that equal to 0 is because we're going to assume that there's no change in the polar direction. Okay? And so any derivatives with respect to theta, we're going to assume it to be 0. Right? Another way that we can state this assumption is we can say that the flow is axisymmetric. Okay? And so axisymmetric flow has no polar dependence. Okay? And so if we cross that out, all that we're left with is 1 over r partial r r u r plus partial u z partial z is equal to 0. Okay. All right, and so let's take this expression and let's integrate it over the vessel cross section. Okay. And of course, we're going to be doing this in polar coordinates too. And so when I say we're going to integrate across the cross section, what I mean is that we're going to take the integral from 0 to big R, okay, where big R is the actual radius of the pipe itself, okay. Okay. Then we're going to integrate by a conversion factor called by 2 pi r, okay. And then we're going to multiply it by whatever we're integrating, okay. Okay, so that dot, dot, dot is, you know, what we plan to integrate. Okay. And our integration direction here is just dr, okay. Okay. And so let's go ahead and do that, okay. And so let's go ahead and apply that term by term. And so if we apply this integral to this entire equation, because we have two terms that are added, we can separate them out into two different integrals, right? And so we're gonna have an integral of the first term and then an integral of the second term, right? And so for the first term there, we have an integral from 0 to big R of 2 pi R. Okay. And we're going to multiply by 1 over R, partial R, ER. My brain and my mouth said R, but my hands like, nah, U. Okay. And so that's the first term. And the second term is going to be same integral. So integral from 0 to big R of 2 pi R. And the thing we're integrating here is partial UZ, partial Z, okay, dr. And the whole thing is going to be equal to 0. Okay. So all I did was I took our conservation of mass equation and then I integrated it, I integrated each term individually from 0 to big R, okay, with the conversion factor of 2 pi R. All right. Let me pause here for a second. So are there any questions on this? Okay. All right. So let's go ahead and continue. And so let's take the first integral first. And so, first thing we see is that since 2 pi is just a constant, and so it doesn't have to be integrated. So we can pull that out of the integral. Okay. Next thing we have here is that we have an R up top and a little r on the bottom. And so these two are going to cancel out. Okay. And so if we evaluate this first integral here, we have 2 pi integral from 0 to big R of partial r of r u sub r dr. Okay. Right. So same thing on the right here. And so the 2 pi I'm going to pull out in front because it's just a constant. Okay. I'm going to do something that if no one's a mathematician in here, right? Okay, because if there was, they would call this sacrilege. But I'm going to take the derivative. I'm going to take this derivative and pull it out in front too. Okay, and so we have partial z. Okay, trust me, I'm an engineer. Okay. All right, and so what we have left is integral from 0 to r u z dr. Okay, and that's going to be equal to 0. Okay. All right. So we have two integrals here, and in the grand scheme of things, these integrals are actually not that bad to evaluate. Okay. So let's start with the first one. And so for the first one, you can see here that we have a derivative with respect to r, but then an integral with respect to r. Okay. And so these two operations are going to cancel out. Okay. Because you can think of derivative as kind of the opposite of an integral. Okay. And so what you have then is you have 2 pi times integral from 0 to big R of d r u r. Okay. Again, this some people might consider this mathematical sacrilege, but I think of it as kind of like a fraction, right? So you have dr up top, dr on the bottom, they cancel out, and so you have just d on top. Okay. All right, and so when you have a quantity like this, right, we had just d something. This is what's known as like a perfect differential. Okay. Again, my brain and mouth said p, but my hands like r. Okay. And when you have a perfect differential like that, you can just when you take the integral of it, you just end up with the argument on the inside. And so what this is this is 2 pi times a quantity, r u r, okay? And we're going to evaluate this at the integration bounds from 0 to r. Okay. Are there any questions on this? Okay. And so we have kind of a nice package here. And so we have 2 pi. And just like any other integral, we're going to evaluate this at those 2 quantities there. Okay. And so we're going to evaluate the integrand here at r first. And so we have big R. We plug that in for little r. And we have UR at r. Okay. Minus 0 times UR at 0. Okay. Of course, we're going to cancel out the second term because we have 0 multiplied by something. And so that 0 is going to cancel that out. And so all we're left with here is R times UR at R. Okay. And so let's look at this quantity right here. And so the fact that it's u sub r tells us that it's the radial velocity. And so it's the velocity of the fluid evaluated at the vessel wall, right? And so if we have a blood vessel like this, okay. UR is whatever velocity is happening in this direction, right? And when we evaluate it at the wall right here, okay, the fact that we're evaluating the radial velocity at the wall means that this UR of R right here is the same as the wall velocity. Right? Because remember, we assume that our walls can move, right? So we have deformable walls. And so when we evaluate the radial velocity at those walls, that tells us the velocity at which the wall is moving, right? Because if you imagine these blood vessels, they're kind of, breathing up in, outwards and inwards, right? And so that breathing motion, we can quantify that with the wall velocity, okay? And so one way that we can express that is we can say that the UR of R is the time rate of change of the vessel radius, okay? And so remember, our vessel radius is big R, okay? And so its time rate of change would just be the derivative of R with respect to T, okay? And so what we have here is that UR of R is equal to partial R partial T. Okay. All right, so let's go ahead and plug that in. And so we have 2 pi times R times partial R partial T. Okay. I know it's been a lot of calculus today so far, but we're going to do another calculus thing. What I'm going to do here is I'm going to do what's called it's called the pro gamer move, but it's actually the reverse chain rule. Okay. And so I think probably everyone's familiar with what the chain rule is. And so we're just going to do the same thing, but in reverse. Okay? I told you it's a lot of math today. Right. And so I'll show you the result, but then but I think if you look at it the other way, I think you'll see the same thing. Okay. Right. And so if we reverse chain rule, these two quantities right here, the R partial T, right? We end up with partial T of R squared. Okay. And so if you carry this forward, and so you take partial T of R squared, right? And we assume that R is a function of T, and we apply the chain rule, then we get what's above. And so I just did the same thing, but in reverse. Okay. Oh, actually, it eliminates the 2 as well, right? Because if you take the derivative of R squared, you end up with the 2 in front. And so that 2 kind of gets gobbled up in the reverse chain rule. Okay. So we've been working on this term a lot, and we're almost done, I promise. Okay. What I'm going to do, oops, not that. Come back. Okay. What I'm going to do is I'm going to take this pi and then move it inside the derivative as well. Right? So pi is a constant, and so pi can move in and out of derivatives and integrals however it pleases. Right? And so what we have is partial t of pi r squared. Okay. And what is pi r squared? Pi r squared is simply just the area of a circle, right? And so what we have here is we plug in area. Whoa. Okay. We plug in area for that. Then what we get is the partial derivative of area with respect to time. Okay. And all that started from this integral up here. There's a lot of work to get here, but it's in my opinion, I think it's a satisfying result because we get something that's relatively simple. Okay. All right. So any questions on how we evaluated that integral there? Okay. So we had to do a lot of kind of mathematical tricks to get there, but hopefully the result was satisfying. Okay. All right, so now let's look at the other integral. The other integral is not nearly as bad, I promise. Okay. All right, so the other integral, we have 2 pi times the partial derivative with respect to z of r uz dr. Okay. All right. And so I know we moved this 2 pi out, but I'm going to move it back in here. Okay. And so we have a partial z of integral from 0 to big R of 2 pi r uz dr. Okay. So this particular integral should look familiar, right? Because what we're doing is we're taking the axial velocity and we're integrating it over the cross section, right? And so another way that we can express this, if you remember from our lecture on review of fluids, this is the same thing as Q, right? And so we take uz, we integrate it across the cross section, we end up with q. Right? And so this integral here just becomes simply partial q, partial z. Okay. Much simpler than the other case, right? A lot less hoops to jump through. Okay. And so if we take that into consideration, and we take our result from down here, we can express the 1D version of conservation of mass. Okay. And so the 1D version of conservation of mass is partial A, partial T, plus partial Q, partial Z, and that's equal to 0. So a relatively simple result, but it took quite a bit of work to get here. Okay. All right, and we have two of our unknowns kind of showing up in this equation, right? So we have our cross-sectional area and we have our flow, right? Remember when we started, we wanted to manipulate these equations in order to get it to be like that. Okay, so this is kind of a really nice, tidy result for what we're trying to accomplish for our equations here. All right. Any questions on this? Yeah.
So is this equation kind of saying that the flow rate with or actually the area of the vessel kind of reacts to the flow rate of the bin?
Exactly. Yep. Yep. So what this is saying is that if you have a change in flow rate along the center line of the vessel, right? And so that's what the partial z is. Okay? And so if you measure the flow at one cross section and it's different from somewhere down here, the only way that that can be compensated is if the vessel expands or contracts. Yeah, and that's just conservation of mass, right? And so same thing, the same thing as well. So if you have a vessel here that's smaller than the vessel out here, then the only way that that can happen is if the flow rates there are different, because you have one that's expanding and one that's contracting. Yep. All right. Any other questions on this? Okay. So I want to, before we jump into momentum, because that'll be a big journey. So before we jump into momentum, I want to talk about the area a little bit more. Okay. And so we've talked about area, from the sense that it's really cool that it's an unknown, right? Because it allows us to do deformable walls, but it also reflects a lot of really other important qualities of the cardiovascular system as well. Okay. And it ties into kind of what we just finished talking about in terms of cardiovascular diseases. Okay. Because if you remember, when we were talking about cardiovascular diseases, a lot of them have to do with the fact that, they're unnatural changes in the vessel and the radius of the vessel, right? And so the first one that comes to mind is stenosis, right? And so if you have atherosclerosis, you have plaque, that's going to cause a narrowing of the blood vessel, right? Okay. Okay. On the opposite side of that, we have an aneurysm, which is the exact opposite, right? Okay. And so an aneurysm is a expansion of a blood vessel. Okay. We can now model that, with our area. Okay. And one other thing that we can kind of really naturally model now is the fact that blood vessels will taper as you flow along the system. Okay. And so all that basically means that as you kind of go away from the heart, right, and so you flow along the aorta and you go to all the branches, the cross-sectional area of the vessel kind of just naturally gets smaller and smaller. Okay. All of these things are possible now, now that we're solving for the area in our equations. Okay. All right, so you guys ready to jump into the momentum equation? All right. All right, so let's look at the momentum equation. So let's start with the Navier-Stokes. All right, and so if you know Navier-Stokes, there's three components of momentum, right? So we have the momentum in the R direction, in the theta direction, and the Z. For this situation, we're only going to consider the momentum in the Z direction. Okay. Even this is going to be a handful because it's going to be 1, 2, 3, 4, 5, 6 integrals we need to do. All right, but let's start with just Navier-Stokes. And so Navier-Stokes in the cylindrical coordinates is going to be partial UZ, partial T. Okay. UR, partial UZ, partial R. Okay. Plus U theta divided by R partial UZ partial theta, okay, plus UZ partial UZ partial Z, okay, plus 1 over the density, rho, times partial P partial Z. Okay, so that's our pressure gradient term. And so all this is equal to our viscous terms. And so we have a viscosity divided by R, partial R of R, partial UZ, partial R, okay, plus viscosity, partial squared UZ, partial Z squared, okay, plus viscosity divided by R squared, partial squared UZ, partial theta squared. Okay. Right, so that's the momentum equation in differential form for cylindrical coordinates. Okay. And so I tell this to all my fluids classes, but you know, I think I told you guys already too that when I first started the job here, I got my apartment before my at the time she was my girlfriend, now she's my wife, and so I named my Wi-Fi Navier-Stokes because I think it's a great equation, it's a beautiful equation, and the whole time, you know, my wife thought it was some kind of dirty joke, you know, for engineering. I'm like, it's not, it's just an equation. And so when we moved about a year ago, and so she didn't let me name the Wi-Fi anymore. But I still love Navier-Stokes. I think it's really cool.
The more you explain it, we're kids.
Yeah, I've stopped. I tried showing her the equation, but you know, she doesn't understand. She just doesn't understand. Okay. All right, so just like we did with the conservation of mass, we're going to integrate this guy across the cross-sectional area. But let's save ourselves some trouble. So let's cross out some of these terms. Okay? And so if you notice, you know, we have some terms here that depend on theta. Okay, and so we're going to cross out this term with the same assumption that we had before, which was our axisymmetric assumption, right? And so any derivative with respect to theta is going to go to 0. And of course, that's going to be true for this one too. So even though it's a double derivative, it still counts as a derivative. So your partial theta is equal to 0. Okay. All right. And so, you know, we're going to integrate every single one of these terms, you know, across the cross section. And so instead of kind of showing all of it right here, what I'm going to do is I'm going to label each of these terms. And so I'm going to use a different color for that. And so we'll call this term number 1. This one will be term number 2. Okay. This will be term number 3. This will be term number 4, the pressure term. Our first viscous term will be term number 5. And then this last one will be term number 6. Okay. And so what I'm going to do is I'm going to go through one by one, you know, how to evaluate these intervals. Okay. Any questions on that before we start? Okay. All right. So let's go ahead and get started. So let's start with the unsteady terms. This is one of the easiest ones. Okay. So term number 1. So for this one, we have 2 pi integral from 0 to big R of partial UZ partial T times R dr. Okay. We're going to perform mathematical sacrilege again, and so I'm going to take the time derivative and pull it out of the integral. Okay, so partial T of integral 0 to R of R UZ times 2 pi dr. Okay. Once again, we come across this integral, and so this integral here, remember, is our flow rate Q. Okay. And so this first integral here, you know, it's fairly easy to evaluate. We just end up with partial q, partial t. Okay. And so the time rate of change of the flow, you know, that comes out of our unsteady term. Okay. And so that makes sense, right? And so our first unsteady term is just the derivative of uc with respect to t. And so when we integrate that across this cross section, we instead get the derivative of q with respect to t. All right. Let's do term number 2. So term number 2, we have a 2 pi integral from 0 to big R of uz, partial uz, partial z, dr, okay, rdr, excuse me. Okay, and so I'm going to do a reverse chain rule on this again. Okay, it's if we have a question, or was it? Oh, I'm sorry. Yeah, so it should be oh wait, hang on. Oh, I'm doing the wrong integral. That's why. Wait, hang on. Cross that term out too. Yeah, so this is number 3. Oh, I'm sorry. Yeah, this is number 3. So I reordered it in my notes for some reason. So let's do number 3 first. I swapped the order of those 2 terms in my notes for some reason. Okay. And so I'm going to do a reverse chain rule on this again. And so this will be a pi integral from 0 to big R. I do this one first because it ends up being a little bit easier. And so we have a partial z of uz squared r dr. Okay. And I'm going to put a box around. That. All right. So this integral is not complete yet, but we need to kind of work through the other integrals first before we can really tackle it. And so I'm just going to leave that one. We'll just leave that one alone. Okay. But we will come back to it. All right. So now let's do integral 2. Okay. And so for integral 2, what we have is we have an r, ur, hang on, forgot the integral. We have a 2 pi times integral 0 to big R of r ur partial uz partial r dr. Okay. Okay. So this one's going to be a bit of work. And so before we actually integrate, you know, let's look at the integrand first. Okay. All right. And so I'm going to come about this in kind of an indirect way. And so, you know, what we see here is we kind of see 3 things multiplied by each other. So we have an R, which is the radial component, okay, or radial direction, multiplied by UR, multiplied by partial UZ, partial R. Okay. And so I'm going to do kind of a reverse product rule here. And so let's say, you know, to kind of help us out with that, let's take this expression here. So let's take partial R of R, UR, UZ, okay? And let's evaluate this according to the product rule, okay? And so this one's interesting because we actually have 3 terms here, but I'm still going to use just the product rule for 2 terms, okay? And so the first term I'm going to get is exactly this expression right here, okay? And so if we apply the derivative just to the uz term, we end up with r ur partial uz partial r. Okay. And then because of the product rule, we're going to have uz, which is the one that we took the derivative of already, but now that's going to be on the outside. And then partial r of r u r. And so this equal sign here, I basically use product rule. Okay. Does that make sense about how I did that? I know it kind of seemed like I pulled I pulled this first term out of my ass, and I kind of did, but you know, just kind of trust me for now. Okay. Any questions on this? Okay. All right, and so let's take this expression and just isolate this first term right here. Okay, and so I'm going to subtract this term from both sides. Okay, so I'm going to take a minus uz partial r of r u r. Okay, and so if we do that, we get partial r of r u r u z minus uz partial r r u r, okay, is equal to r u r partial uz partial r. Okay. And so we need to go one layer deeper, okay? Because when we see this term right here, we can actually come up with another expression for this term using our original continuity. Okay?
Wait, sorry, did you just move that whole term to the left?
Yes, yeah. And so I basically took this term right here and I moved it to the other side of the equation. Yeah. So that's why it has a minus sign here. Okay. And so if you recall from our conservation of mass equation, so let me go ahead and write that again. Okay. And so this is like flashback. Okay. And so flashback from I guess 20 minutes ago. Okay. Our conservation of mass equation in cylindrical coordinates was partial uz partial z plus 1 over r partial r r u r. Okay. I'm gonna go ahead and assume that the what's it called? That the polar term is 0. Okay. And so there's no d theta. Okay. And so our conservation of mass equation look like this. Okay. And so if you notice, this is the same as this, right? And so let's use this expression to solve for that. Okay. Okay. And so if we solve for this expression in our conservation of mass equation, then what we get is partial r is equal to our partial r of r u r. Okay, this is equal to minus r partial uz partial z. Okay. And so let's take this and let's substitute that back up here. Okay. All right. And so we substitute that back up there. What we get is partial r of R U R U Z plus R U Z times partial UC partial Z. Okay, this is equal to R U R partial UZ partial R. Okay. And so this expression right here, this line is the same as this line, right? The only thing is I just made a substitution in there for the conservation of mass. Okay. All right. So any questions on how we obtained this so far? Okay. All right, so now that we have this, we can go ahead and plug it, we can plug this back into the integral, okay? Because if you remember, where we started, we were trying to find the integral of this guy right here, okay? And so let's go ahead and plug that back in. Okay, so this will be for integral 2. Okay. All right, so we plug that back in. What we get is 2 pi, okay, integral from 0 to big R of this whole quantity right here, okay? And so we have partial R of R U R U Z, okay, plus R U Z partial U Z partial Z, okay, dr. Okay, and so I'm going to go ahead and split these into 2 integrals. And so for the first integral, we have 2 pi, integral from 0 to big R, of partial R, of R U Z U R dr, okay, plus 2 pi, integral from 0 to big R, of R U Z partial Z dr. All right. So time for more mathematical war crimes. And so let's take this first integral. Right. So we have dr on the bottom, dr up top. And so let's just go ahead and cancel that out. And what we're left with is 2 pi times integral from 0 to big R of d R U Z U R. Okay. How do I sleep at night knowing mathematicians walk among us? It's a good question. I don't. I just I sleep with one eye open. Okay, and so what we have here again is a perfect differential. Okay, and so what we get from this is 2 pi times the quantity R U Z U R. And we're going to evaluate this at the bounds of the integral, okay? And so R and 0, right? Just go ahead and do that. And so we have 2 pi times big R times UZ at R times UR at R, okay? Minus 0 times UZ at 0 times UR at 0, okay? Right. Oh, my stylus was getting ahead of me. And so, we have a 0 multiplied by this stuff. And so we're going to go ahead and cancel that out. Okay. If 0 multiplied by anything is still 0. Okay. And believe it or not, we're going to cancel this term as well. Okay. Because this term right here, this is our axial velocity at the vessel wall. right? And so this is important because this is basically the velocity that's going down the vessel length, you know, evaluate at the wall. And so if we kind of draw a vessel like this, okay, remember UZ is going this way, right? Okay, but we're going to evaluate UZ at the vessel wall right here, okay? And so right here is R is equal to big R. And what we're going to assume, you know, even though we have deformable walls, right? So we've already seen that the walls are going to move. We're only going to assume the walls are going to move in the radial direction, right? And so they're not going to do any kind of worm-like stuff. They're just going to kind of, you know, undulate in place. And so they're going to expand and contract only in place, right? And so if we assume the wall motion is purely radial, then that means that the axial velocity or the centerline velocity at the wall, we're going to assume that to be 0, okay? Okay. And the justification for that is we're going to assume that we have a no-slip boundary condition. And so this term is also going to go away, okay? You know, a mathematician will be proud of this. And so we did all this work just to show that something is just 0, right? That's pure, if that's not pure mathematics, then I don't know what is. Okay. And so that's great. And so that means that first integral that we have up here, this whole thing is just going to be 0. And so all we're left with is just the second integral here, okay? And so if we work through the second integral, this is going to be a lot faster, okay? Yeah.
Is that just because
yes, it is dependent on R, but we're going to assume that when you evaluate it at big R, which is the wall, it's going to be 0. And so that's our no slip boundary condition. Remember, because we ended up with the perfect differential here. So it's not like we're integrating UZ across R. We're only evaluating it at the wall, and we're evaluating at 0. And so since we're only evaluating at the wall, then we end up getting 0 for that.
So, sorry, what's the difference between the other situation with RR?
Mm-hmm.
At that point, we didn't have the no-slip condition. We decided to just change it.
Right. And so the difference between, and so, you know, and so that situation is actually right here, right? And so, you know, we have this R U Z, right? But we don't have a perfect differential here because the D, right, the differential is on the outside here. And so this means that we're integrating it across the entire cross section. But since for this one, mathematically, we only had this perfect differential here, that means we're not integrating it over the entire surface. We're only evaluating it at the wall and at the center. And so because of that, you know, we can cancel that. We can cancel that out. Let's we can talk after class. I know the math details in this section is a lot, and we're not even done yet. Okay, and so what I'm going to do is I'm going to take this 2 and I'm going to bring it on the inside. Okay, so we end up with pi integral of 2 uz partial uz partial z times r dr. Okay. For this thing right here, I'm going to do a reverse chain rule. Okay. And so we end up with pi integral from 0 to big R of partial z of uz squared r dr. Okay. And then we'll stop there. Okay. And so does this, and so maybe this box guy looks familiar, or maybe not, because we've been looking at symbols kind of all day today. But if you go back up to our integral for integral 3, right? It's the exact same thing, right? And so we end up, so integrals 2 and integral 3 actually end up being the exact same thing once we kind of work it through it mathematically. Okay, and that's not a coincidence. And so, you know, what we'll do next week is we'll pick this up and we'll talk about what we can actually do with this term, as well as the other three integrals that we have yet to evaluate. Okay, but it is 5:15. You know, I would love to continue, but you know, even though there's only so many math war crimes, I guess we can commit in one day, and so we'll do more war crimes on Tuesday. Okay. All right. So thank you everyone for tuning in today. I know it was a lot of math today, but you know, I try to kind of keep it upbeat as I can. So make sure you select your model before midnight tomorrow, and then I can send you your medical image data so you can work on that project. Okay. So thank you everyone for tuning in. You know, hope everyone has a good weekend, and I'll see you guys next week. Thanks, guys.
So you're just saying that because that perfect integration.
Yeah.
Mm-hmm. So that's just dependent on UR, but now we have two dependencies on UR.
Exactly. So it kind of depends on how the integral ends up being. And so if you look at this is a good example. And so here we have UZ, but we're integrating this over the entire circumference. So that's going to depend on how UZ varies integrating from 0 to 8. Right? And so we're covering that entire distance. So only when we have this. So when we have yes, so when we have this, then you know you can think of it as almost like the integral of canceling out this. Because normally you don't have this in an integral. So in an integral usually you have stuff multiplied by PR, and that's why you put form like antiderivative and plug in for the. But since we have this d right here, right, then this kind of cancels out with the integral, and so you don't have to perform an antiderivative. So you just kind of stick right to the part of the value of this. And so this expression right here, and so this is kind of what we end up with, right? Yeah. And so this is, imagine that this is you know, when you perform the integral, usually you kind of get to this point after you perform the antiderivative. Yeah. But for this one, because we have the perfect differential there, we kind of skip right to this point. And so when we do this, this ends up being, right? And so when you get to this point, you evaluate whatever's left right here.
Yeah, it's just RU.
Right. Minus 0 times UR. And so that's and so you know, when you have that perfect differential, you know, UR is varied across all, but we're just not integrating because we ended up with the perfect differential. And so that's why we just evaluated that. It's more mathematical than it is.
I see, yeah, because I was trying to understand it based on what you're describing within the recipe. So then, oh, so based on what you just said, we're not integrating, right? It's still varying. So that's why.
Exactly.
That's why it's still changing over time.
Exactly. And this is U on. And so the one that we're looking at is UZ. So UZ is 0. UR is
okay. Yeah, so okay, so UZ doesn't vary within time because we're actually
it can vary in time, but at the wall, you know, when you evaluate this at the wall, it's going to be 0.
Oh, okay. Now I'm understanding.
Yes, yeah. So UZ it's definitely going to vary with time. Bye, guys.
And it would vary kind of like radially too.
Exactly. Yes.
Okay, but then at the wall, we're saying it's 0 because of no slope.
Exactly. Yes.
Okay. All right. Thank you.
Yeah, it's a lot to wrap your mind around.
Yeah.
It is a lot. So I'm
Okay.
glad you're asking.
All right. Thank you.
Yeah. All right, Romong, any final questions before I wrap it up for the week? Okay, all right, so I'm going to sign off. Have a good weekend.